Let's have a look at this question. You can see in the question what we have to do is, you can see we have to find the compound that will produce 1,5-cyclooctane dione on ozonolysis. And you can see we have 4 options with us. Very interesting question. Let us see how to solve such kind of questions. So here, as you can see in this particular case, we have the product already given to us, isn't it? The product is already mentioned, and that is 1,5-cyclooctane dione. Now let me tell you, in ozonolysis, first of all, what we do is we have a reactant which is made to react with O3, and thus it will form an ozonide intermediate. And let's take an example of the reactant as well. All right, so let's say we have a reactant which is CH2 double bond CH2. Now it is made to react with O3 and it will form an ozonide intermediate which will look like this. You can see CH2 and then O, and then here CH2 and then connected with this. Okay, so now you can see this is forming an ozonide intermediate which then is made to react in the presence of zinc and water, and thus what will happen, it will give you 2 molecules of formaldehyde CH2O, or let us write it better. Let us write it in a better way. What it will give you is HCHO, 2 molecules of it. All right. So this is what takes place in case of ozonolysis, and important thing to note here is that ozonolysis can be of 2 types. One is reductive ozonolysis, other is oxidative ozonolysis. All right. Now if you use this zinc, then the ozonolysis is called as reductive ozonolysis, and if you do not use this zinc, then the ozonolysis is called as oxidative ozonolysis. All right. So now you can see in this case, since we are getting dione as the product, that means we are getting ketones as the product. So always remember, if you use zinc, then only your final product will be either aldehyde or ketone. Whereas if you do not use this zinc, then your final product will be a carboxylic acid. All right. So by looking at the product, one thing we can say is that here we are talking about reductive ozonolysis and not oxidative. All right. Now let me tell you a trick to solve such kind of questions. You do not have to put more time into solving such easy questions, and the trick is very simple and is you can say applicable in all such questions based on the reductive ozonolysis. So let me tell you the trick. What you have to simply do is, about the pi bond, let's say we were talking about this particular alkene. So about the pi bond, what you have to do is this CC pi bond, you have to break this pi bond, and then you have to add a double bond O here as well as a double bond O here. All right, and what you will get will be straight away your product of the process. All right, so now you can see here in this case you are getting HCHO and 2 molecules of it from 1 molecule of alkene, isn't it? So this is a very simple trick. Now let's use this trick in order to solve this particular question. So now you can see, if I use this trick in case of option A, then what I'll do is I'll simply break this bond and I'll put double bond O here and double bond O here. Now by doing so, one thing you can analyze is, in this case the final product will have only this 5-membered ring, isn't it? That means it cannot be cyclooctane. So option A definitely cannot be the answer. Moving to option B, here if you break it from here and you put double bond O and double bond O here, what you will get is an 8-membered cyclic system, isn't it? Wherein you can see this is number 1 carbon, number 2, number 3, number 4, number 5, number 6, 7 and 8. So one thing is very clear, that this is cyclooctane, and yes, it has 2 ketone groups also. So therefore it has to be cyclooctane dione, that is for sure. Now if you see the locant of these C double bond O, or you can say these ketone groups, then you can see one of it is at locant 1 and the other one is at locant 5. So definitely the name of this product will be 1,5-cyclooctane dione, which is what we were looking for. So definitely option B has to be the answer. All right, so moving to option C, if you break it from here and put double bond O here and double bond O here, then clearly you can see that there will be no longer a ring existing in the product. So definitely this cannot be the answer. Moving to option D, now you are breaking it from here and you are adding double bond O here and double bond O here. Again you can see there is no ring in the final product. So obviously this also cannot be the answer. So clearly you can see that the right answer to this question is option B. Hi, let's have a look at this question, and you can see in the question we have 1 mole of symmetrical alkene which is made to undergo ozonolysis to give 2 moles of an aldehyde with a molecular mass of 44 U, and you have to find the alkene. Very, very interesting question. So first of all, one thing is clear, the alkene is symmetrical. All right, symmetrical alkene, let's look for the symmetrical alkenes in the option first of all. So in option A we have ethene. So you can see ethene is definitely symmetrical. So this can be the option, or you can say this can be the right answer. Now moving to option B, which is propene. So you can see propene is like this, CH double bond CH2. Clearly you can see that this is not symmetrical, so obviously option B cannot be the answer. Moving to option C, it is but1ene. Let's draw the structure. So it is CH2, CH, CH2 and CH3. So clearly you can see but1ene is not symmetrical, so this cannot be the answer. And option D is but2ene. So you can see but2ene will be like this. So yes, it is symmetrical. So yes, we can say that option A and D could be the answer, isn't it? Any one from the A and D. So now let's find out which one will be the answer. Is it A or D? So now what you have to do next is, you can see since you are getting 2 moles of aldehyde, one thing is clear that you are going for reductive ozonolysis, wherein you are using zinc that will scavenge the extra oxygen, thereby leading to aldehydes or ketones as the major product. Otherwise, if let's say you would not have used zinc, then you would have get the you can say carboxylic acids as the major product. All right. So now let's see how to find out the answer to this. One thing all we know is that the molecular mass of the you can say alkene is 44U. Sorry, not alkene. The molecular mass of the aldehyde that you are getting is 44U. Okay, so let me tell you a trick to solve such questions. What you have to do is, you just have to break this CC double bond and you have to add double bond O here and double bond O here. All right. So what you are getting in case of option A, that is ethene, is 2 molecules of formaldehyde, isn't it? So let's now match the molecular mass. All right, let's now calculate the molecular mass of formaldehyde. So we know that in case of formaldehyde, the formula is HCHO. And here you can see 12U from carbon, and then you have 2U from 2 hydrogens and 16U from oxygen. So this means a total of 12 plus 16 plus 2 becomes 30U. So the molecular mass for aldehyde is 30U, which is definitely not matching with what is given in the question. So option A cannot be the right answer. So left with us is only option D. Definitely it has to be the right answer. But let's calculate the products and their molecular mass. So now you can see again we have to break this C double bond C and we'll put double bond O on both the sides. So what are we getting is acetaldehyde. Now let's measure the molecular mass of acetaldehyde. So now you can see here we have 2 carbons, so 24U from carbon. Then we have 4 hydrogens, so 1U from each hydrogen, that means 4U in total. And we have 1 oxygen, so 16U from oxygen. And this becomes a total of 44U, which is exactly matching with the data given in the question. So option D is the answer to this question. Hi, let's have a look at this question. In the question, what we have to do is, we have to find out in which of the following anti-Markovnikov's addition of HBr is not observed. Very interesting question. Let us see how to answer. So now you can see we have 4 options here. Let's first write down the structure of these. So propene is CH2 double bond CH, CH3. Now but1ene is CH2 double bond CH, CH2, CH3. And you can see the next one is but2ene. So but2ene is CH3, CH double bond CH, CH3. And pent2ene is CH3, CH double bond CH, CH2 and CH3. Clear? So these are the structures of the, or you can say, molecules given to us in the 4 options. Now let us see how to figure out whether anti-Markovnikov's addition of HBr will be observed in a particular molecule or not. Very simple it is. First of all, you have to understand the definition of Markovnikov's addition and anti-Markovnikov's addition, or I should say, you have to understand the Markovnikov's rule and anti-Markovnikov's rule. So Markovnikov's rule says that this halogen part of HBr will attack on that double bonded carbon which is more substituted. or you can say which carries less number of hydrogens. Clear? And you can say anti-Markovnikov's rule is just opposite of that. That means in case of anti-Markovnikov addition, the halogen part of HBr will attack on that double bonded carbon which is less substituted. All right, so let us simply look for the carbons that are more substituted and less substituted. Now you can see in case of option A, this carbon is carrying a methyl group, whereas this carbon is carrying only two hydrogen groups, which means obviously this carbon is less substituted. So there is a possibility of attack of bromine on this carbon. That means it can show you the anti-Markovnikov's addition. All right, so option A can show, that means it cannot be the right answer. Moving to option B, here also you can see this double bonded carbon is bonded with this ethyl group. All right, so you can see the other one is bonded just with two hydrogen atoms. All right, so you can clearly see that in this case also, if Br attacks on this CH2, that is terminal carbon, then again you will be able to say that the product is according to the anti-Markovnikov's rule. Clear? So here also it is possible, so cannot be the right answer. Moving to option C, here you can see both of these double bonded carbons have one hydrogen and one methyl group, which means you can see this number of substituents is same on both the carbons. None of these is more substituted or less substituted. They are equally substituted. So here anti-Markovnikov's addition will not be observed. So this is the right answer. Moving to option D, here you can see about these double bonded carbons. One carbon is carrying a methyl group, other is carrying a ethyl group, and obviously the remaining are hydrogen atoms. So clearly you can see both are differently substituted. All right, the one that is carrying ethyl group is considered to be more substituted, whereas the one that is carrying methyl group is considered to be comparatively less substituted. So in this case also anti-Markovnikov's addition can be observed. So obviously this also cannot be the right answer. So clearly you can see that the right answer to this question is option C. Hi, here we have a very interesting question, and the question is which alkene on heating. So you can see here we have an alkene and we are heating it with acidic KMnO4. So here we have acidic KMnO4 solution gives acetone and a gas which turns lime water milky. So important clue here is the gas that we are getting is turning lime water milky. Now just keep thinking about this, which gas turns lime water milky. Just try to put little more stress. Yes, are you getting it? Absolutely, it is CO2. We know that it is carbon dioxide that turns lime water milky, isn't it? So now you know that we have acetone and CO2 getting obtained due to this reaction, and what we have to look for is the reactant. So the simplest way is to draw the structure of all four of these, and then let's try to form the product in these cases. All right, so very simple it is. Let's first draw the structure of option A, that is 2-methyl-but-2-ene. So you can see 2-methyl-but-2-ene is this molecule 2-methyl-but-2-ene. Now in this case, if we made it to react with acidic KMnO4, or you can say if we made it to heat in the presence of acidic KMnO4, then what you have to simply do is, I'm giving you a trick here, you have to break this double bond between carbon atoms, and what you have to do is put one double bond over here and one double bond over here. Clear? So by doing so, what you will get is you will get acetone. Clear? Along with it, what you are getting is CH3CHO. All right, but since it is acidic KMnO4, it is a very strong oxidizing agent, and it will further oxidize the aldehyde to give you carboxylic acid. All right, so what you will get here is CH3COOH, that is acetic acid. So now in this particular case, the products are acetone and acetic acid. Clear? Which means this obviously cannot be the right answer. Moving to option B, here you have isobutylene. Let's first draw the structure of isobutylene, and then we will simply use the same trick. So let's do this. Isobutylene is like this, C double bond CH2. Now in this case, if you react it with acidic KMnO4, all right, or if you heat it with acidic KMnO4, what will happen? You have to simply break this C double bond C, put double bond O on both the sides. So by doing so, what you are getting is CH3, CH3, C double bond O. Important thing, always remember during this reaction, the ketones, if gets formed, will not be oxidized further with the help of this acidic KMnO4. All right. So the next product, or you can say the other product that you will get along with acetone, is the formaldehyde. And always remember, whenever you get formaldehyde, then acidic KMnO4 oxidizes formaldehyde further to CO2. All right. So it oxidizes it further to CO2. Clear? And you can learn a trick. What you have to do is you have to break this CH bond, this CH bond as well. And then you have to add, you can say, two OH groups here. Sorry, not two OH group. You have to add one OH group here, because you are breaking one bond only. So one OH group here, one OH group here, and since you are breaking two bonds connected with carbon, so two OH groups here. Now whenever a carbon bears two OH group, then water gets released and leading to formation of CO2 in this case. Clear? So here you can see clearly we are getting acetone and CO2. That means option B is the right answer. Moving to option C, here we have but1ene or 1-butene, you can say. Let's see what we will get in this case. So 1-butene, what we will get is CH2, CH3. Again, you have to break these two bonds. Clear? That is C double bond C. You have to break double bond O here, double bond O here. So what you are getting is two aldehydes in this case. But since the acidic KMnO4 is used, both will get further oxidized to give you what? Let me tell you. See, this propanol will oxidize further to give you propanoic acid, that is CH3, CH2, COOH. But the formaldehyde that is obtained will oxidize further to give you CO2. Clear? And clearly you can see that this is not the right answer. Why? Because we are getting acetone and CO2 and not propanoic acid and CO2. Clear? So this is not right. Moving to option D, which is 2-butene. Let's see what we will get in this case. So 2-butene is CH2 double bond, not double bond. It has to be CH3, CH double bond, CH, CH3. Again, break these, double bond O here, double bond O here. So what you are getting is two molecules of acetaldehyde. But since the acidic KMnO4 is used, which is a very strong oxidizing agent, the acidic, you can say the acetaldehyde will further oxidize to acetic acid. So what you will finally get is two molecules of acetic acid. Again, this is not matching with the products mentioned in the question, so cannot be the right answer. And hence the only correct answer to this question is option B, that is isobutylene. Hi, let's have a look at this question. The question is identify the incorrect statement. So here we have to identify the incorrect statement. Let's have a look at the statements. Now you can see statement 1 is alkynes are more reactive than alkenes towards electrophilic addition reaction. See, let me tell you, this statement is incorrect. All right, alkynes are not more reactive as compared to alkenes. In fact, they are less reactive. There can be two reasons for the same. Let me tell you. The first reason is, if you see some of the you can say electrophilic addition reactions proceeds through transition state or cyclic transition states. All right, and those cyclic transition states in case of alkynes are less stable when compared with the same transition states obtained with alkenes. All right. So therefore we can say that alkynes are less reactive. And the second reason is, let's take an example in order to understand the second reason. Let's say we have a molecule like this, which is ethene, and let's say we have a molecule like this, which is ethyne. Now let us assume that it is undergoing electrophilic addition reaction. All right, and let's say the reaction is with HX. All right, a hypothetical reaction, just in order to make you understand how and why the alkynes are less reactive. All right. So now you can see in this electrophile, which is H plus, will attack first, isn't it? And what you will get as a result is a carbocation. And the carbocation will look like this, CH2 positive, isn't it? Which means here in this case, the carbon bearing positive charge is sp2 hybridized. All right. So it is sp2 hybridized. That means the percentage as character of this carbon is 33.33%. Clear? Now let's see in case of alkynes. So here if the same HX attacks, and then again the electrophile will attack first, that is H plus will attack first. So what you will get in this case is CH2 double bond CH with a positive charge. So now you can see in this case the hybridization of carbon is sp. And now clearly you can see the percentage as character therefore is 50%. And we know that more is the percentage as character, more is the electronegativity. So this tells you that in case of alkynes, the intermediate that you will get, or the carbocation intermediate that you will get, is less stable. Why? Because in this case a positive charge is present on more electronegative carbon. All right, so this tells us why alkynes are less reactive than alkenes. So that means this is the right answer. And moving to the next option, which says alkynes are less reactive than alkenes towards electrophilic addition reaction. Absolutely correct. Just now we discussed about it, so this cannot be the answer. Moving to statement 3, it says alkynes decolorizes bromine water. This is absolutely correct, so cannot be the answer. Let me tell you, bromine water is reddish brown liquid. All right, and basically when it is added to an unsaturated compound, then what happens? The bromine gets added about the pi bonds. All right, or you can say the bromine gets added to the carbon forming pi bonds. All right, leading to decolorization of bromine, and hence it is treated as a test for unsaturation. So yes, alkynes decolorizes bromine water. Moving to option 4, it says addition of HBr to alkenes in presence of peroxide proceeds via Markovnikov's rule. All right, so let us see whether it is right or not. So you can see if we add HBr to alkenes in the presence of peroxide, then yes, then it proceeds via anti-Markovnikov's rule. All right, it do not proceed via Markovnikov, but will proceed through anti-Markovnikov's rule. We know that it is called as Kharash effect. It proceeds through free radical mechanism, wherein we have 3 steps: initiation, propagation, termination. And if you remember, the major product here is through the anti-Markovnikov's addition. All right, so this statement is definitely incorrect. All right, so that means 2 statements are incorrect here. One is statement first and the other one is statement fourth. Now let's look for the options. Now option A says statement 1 and 2 are incorrect. This is not the right answer. This is not right. Moving to option B, it says second and third statements are incorrect. Not right, isn't it? And option third, or option C, says first and fourth statement are incorrect. Absolutely correct. And D says second and fourth are incorrect. Not at all. So that means option C is the answer to this question.